Okay, I'm just going to go through and do some examples of Cauchy-Euler equations. So for the first example, we have 2t times x double prime minus 4x prime plus 2 over t x equals 0. And the first and most important step is to recognize that this is Cauchy-Euler. It's not in the Cauchy-Euler form, so I'm going to multiply everything through by t. And the reason it's Cauchy-Euler form is because I have constant times t, constant, and then constant over t. And when I multiply through by the t, I get 2t squared x double prime minus 4t x prime, and then t's cancel in that term, so I get 2x equals 0. So t squared times x double prime, t times x prime, and everything else is just constants. So now it's in Cauchy-Euler form. And I can make my guess. It's just going to be something times t to the r. C and r are constants, so I'm going to take derivatives and plug it into the equation. So derivative of t to the r is t to the r minus 1. Constant goes for the ride. Derivative of t to the r minus 1 is going to be r minus 1 times t to the r minus 2. And these r and the c's are constants, and they just follow. I'm going to take these results, plug them into the equation, see what that implies about c and r. So 2t squared times x double prime, and x double prime is r times r minus 1, ct to the r minus 2. Second term is 4t times x prime. X prime is r ct to the r minus 1. And then finally plus 2 times x, which is ct to the r. And that's all 0 from my original equation. Let's do some algebra to clean this up. T squared times t to the r minus 2. So we have the 2r times r minus 1 stays the same. This becomes c times t to the r. Here, t times t to the r minus 1, I'm going to get a 4rc t to the r. And then this term I leave alone. And now I notice I've got a ct to the r, ct to the r, ct to the r in every term, so I can factor that out. If you get to here and you cannot factor out a ct to the r, you did something wrong somewhere. You may have not recognized this correctly, or you made an algebra mistake somewhere else. So if I factor those terms out, I have a 2r, r minus 1. Here I have a minus 4r. There I have a plus 2. Okay, this is my assumption from my original equation. I'm assuming that's not 0 or identically 0. So that means everything else has to go to 0. And now if I multiply this through, I get 2r squared minus 2r minus 4r plus 2 is 0. 2r squared minus 6r plus 2 is 0. Okay, I don't immediately see how to factor that, so I'm just going to do quadratic equation. So b is minus 6, so minus a minus 6 is 6, plus or minus 6 squared, minus, so a is 2, c is 2, all over 2a, which gives me 2 times 2. So let's clean that up. So I get 6 plus or minus. This becomes 36 minus 16 all over 4. So this becomes 6 plus or minus. So that becomes 20, square root of 20 over 4. So my solution then is C1 times T, and I'm going to go, I have two solutions for my R, so I can just take a combination. So I'm going to have 6 plus square root of 20 over 4 for that exponent. And for the second exponent, I'm going to use the 6 minus square root of 20 over 4. So square root of 20 is 4-ish. So both of these are positive. This is my dominant term, because that's the bigger exponent. So this thing is going to grow like t raised to the 6 plus 20 square root of 20 all divided by 4. All right, so we expect to see growth in this solution. Okay. Let's look at our next example. We have t x double prime plus 3x prime minus 3 over 2x is 0. Again, first step, anytime you see a differential equation, is try to figure out what kind it is. and that's going to help guide us decide. So it looks like I've got descending powers at t by the derivative. So I'm going to multiply everything by t. If I do that, if I distribute that t, I see it is now in Cauchy-Euler form, and I can do my assumption. I get ct to the r. I'm going to plug this in. So I need to take the first derivative. So I get r times c t to the r. Second derivative. Oops, that should be a minus 1. When I take the derivative, the r comes down, I reduce that. So I'm going to bring down the r minus 1, and I'm left with c times t raised to the r minus 2. I'm going to plug this into my differential equation that's in Cauchy-Euler form, so I get t squared times x double prime. So I get the r times r minus 1 times ct to the r minus 2 plus 3t times x prime, that's r ct to the r minus 1, minus 3 times x, and x is ct to the r. Let's do my algebra. T squared times t to the r minus 2 is t to the r. T to the r minus 1 times t is t to the r. And I'm going to leave the final term alone. Oops, that should be ct to the r. Let me rewrite that because that's now a mess, sorry. Do my check. I get ct to the r, ct to the r, ct to the r, so that can be factored out. And what's left behind is my r times r minus 1 plus 3r minus 3. I don't want ct to the r to be exactly 0 because that's my solution. So I get r times r minus 1 plus 3r minus 3 is 0. So let's expand everything out so that becomes r squared minus r. And I'm left with the 3r minus 3 minus r plus 3r becomes plus 2r. And I believe I can factor that. It's going to be r plus 3, r minus 1. Is that correct? So it gives me a 3r minus r is 2r. 3 times minus 1, yep. So I get minus 3 and 1, so this one comes out to be nice. So my dependent variable is x. I get two solutions. So I'm going to have c1 t to the minus 3 plus c2 t to the 1. This thing decays in time. This thing grows like t. So after a long time, this goes to 0, and I'm just left with this. So my solution is going to grow, and the dominant term is t. Another example. 4t x double prime plus x prime minus 1 over t x is 0. Again, it's almost Cauchy-Euler, but my powers aren't quite right, so I'm going to multiply everything by t. So I get 4t squared x double prime plus tx prime. T divided by t is 1. Now it's in Cauchy-Euler form. I can make my guess. So it looks like c times t to the r. I'm going to take my first derivative. So I get r times c to the tr minus 1. Second derivative, get r times r minus 1 times r times t to the r minus 2. Plug it into my equation. So I get 4t squared times x double prime. That's r times r minus 1 ct to the r minus 2 plus t times x prime. That's r c times t to the r minus 1 minus x, and that's ct to the r is 0. Collect my like terms, so I get 4r r minus 1 times ct to the r, because t squared times r, t to the r minus 2 is t to the r. Here I'm going to get r ct, t times t to the r minus 1 is t to the r. And I leave the last term alone. Again, if you don't get to here and you do not see a ct to the r in every term, you made a mistake somewhere. I can factor that out. I know I don't want that to be 0 because that's my solution. What's left behind is 4r times r minus 1 plus r minus 1. So that means that 4r times r minus 1 plus r minus 1 has to be 0. And let me expand everything out. So multiplying the 4r through, I get 4r squared minus 4r plus r minus 1 is 0. I'm going to collect like terms. So minus 4r plus r is minus 3r. Leave the minus 1 alone. Oh, great. Okay. Yeah, again, I don't see an obvious way to factor that, so I'm not going to mess around. Just use the quadratic equation. B is minus 3, so minus a minus 3 is 3. So I'm going to have minus 3 squared minus 4 times, in this case, a is 1 and c is minus 1. All over 2 times a, so 2 times 4. So let's clean that up. So minus 3 squared is 9. This becomes minus 16 times minus 1 is plus 16. Oops. 3 squared is 9, not 9 squared. 2 times 4 is 8. So that becomes 3 plus or minus square root of 25 over 8 is 3 plus or minus 5 over 8. So when I have the plus, 3 plus 5 is 8 over 8 is 1. Or when I take 3 minus 5, I get minus 2 over 8. And that I'm going to write later as minus 1/4. So my solution then is going to be C1t, and I'm going to use the first root. That's 1 plus C2t raised to the second, which is minus 1/4. So this term decays. As t gets really big, that's going to slowly go to 0. And this is going to grow. So my dominant term is t. So my solution grows like t. Let's do another example. Let's do minus t x double prime plus 5x prime minus 3 over 2x is 0. Once again, it's not Cauchy-Euler, but it's like it. But if I multiply everything through by t, I get minus t squared x double prime plus 5t x prime minus 3. The t's cancel, so I get minus 3x is 0. Now it's in Cauchy-Euler form. Now I can make my assumption that it looks like c times t to the r. C and r are constants. I'm going to take the first derivative. So I bring the r down, and I get t to the r minus 1. Take the second derivative. So I'm going to bring the r minus 1 down. So I get r times r minus 1 times c, and the exponent becomes r minus 2. Plug this into my equation. Again, I'm plugging it into the Cauchy-Euler form. So I get minus t squared times x double prime. So that's r minus 1, ct to the r minus 2, plus 5t times x prime. So that's rct to the r minus 1. Minus 3 times x, and x is ct to the r, is 0. I'm going to go through and collect like terms. T squared times t to the r minus 2 is t to the r. And I have to take the minus r times r minus 1, leave it alone. I have 5rc. T times t to the r minus 1 is t to the r. Leave the last term alone. And, oops, I forgot my c. This c should be there. So I get ct to the r, ct to the r, ct to the r. It's in every term, so I can factor it out. I'm left behind in minus r times r minus 1 plus 5r minus 3. This is my assumed solution. I don't want that to be 0. So that means I have a minus r times r minus 1, minus r times r minus 1, plus 5r minus 3. That has to be 0. Let's expand this out. This becomes minus r squared plus r plus 5r minus 3 is 0. So I get minus r squared plus 6r minus 3 is 0. Again, I don't see an obvious way to factor that. So r is, my b is 6, so I get minus 6 plus or minus b squared minus 4. A is minus 1. C is minus 3. all over 2 times my a, which is minus 1. So let's clean that up. 6 squared becomes 36. Is that correct? Yes, that becomes minus 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 is minus 4 times 3, so I get minus 12 all over minus 2. So my r is minus 6 plus or minus. This becomes 34/24 over minus 2. So my two roots are minus 6 plus square root of 24 over minus 2, or minus 6 minus square root of 24 over minus 2. So I'm working with x's. X is going to be c1t. The first one is minus 6 plus square root of 24 divided by 2 plus c2t. Oops, I got to be careful. There's a minus 2 in the denominator. Minus 6 minus square root of 24 over minus 2. Because of this minus 2, if I bring that up, that cancels. 6 plus square root of 24 is going to be the bigger of the two things. So my solution is going to grow like 6 plus square root of 20, t raised to the 6 plus square root of 24, all divided by 2. All right, one last example. This last example is going to give us a double root, and what we're going to find is that we can't just multiply by t anymore. It's not going to work out so nice. So what we're going to do is we're going to end up using reduction of order and see what happens. So if I have this differential equation, I have to recognize it's not constant coefficient. I'm going to hope it's Euler, Cauchy-Euler. Notice if I multiply everything by t, it is now in Cauchy-Euler form, so life is good. I can make my assumption that x is c times t to the r, so I'm going to take two derivatives and plug it in. So I'm going to bring down the r for the first derivative and get t to the r minus 1. For the second derivative, I'm going to bring down the r minus 1. And when I reduce it, I get to r minus 2. We plug this into our equation. So t squared times r minus 1 times ct to the r minus 2 minus t times first derivative is rct to the r minus 1 plus x is ct, just x, ct to the r is 0. I'm going to collect my right terms. So this becomes t to the r minus rct to the r plus ct to the r is 0. ct to the r, ct to the r, ct to the r in every term, so I can factor it out. What's left behind is r times r minus 1 minus r plus 1. I don't want that to be 0 because that's my solution. So that means I want r times r minus 1 minus r plus 1 equals 0. Expand everything out. Can't expand anymore, so now I'm going to collect like terms. And I get r squared minus 2r plus 1, which I like because I can factor, but I get a double root. So that means my x is going to be c1. Oops, so that says r is 1, so t to the 1. I need two roots because I got two derivatives, or two homogeneous solutions. Turns out I can't just multiply through by t. If I do that, it's not going to work. So I'm going to use reduction of order. So I'm going to assume my x looks like u of t times t because that's my homogeneous solution. So let's play the game and see what that implies. So my differential equation is t squared x double prime minus tx prime plus x is 0. I've assumed that x of t is u of t times my homogeneous solution, which is t. Now I'm going to take two derivatives and plug it in, but now I got to use product rule. So the derivative here is going to be u prime times t plus u of t times the derivative of t, which is 1. Now when I take the second derivative, I have to use the product rule again. So this becomes u double prime times t plus u prime, derivative of t is 1. And now here I don't have to use the product rule anymore because that just becomes u prime. So let's simplify that. So I get u double prime times t, and I've got 2 u primes. If I plug this into my equation, I'm going to have t squared times x double prime. It becomes u double prime times t plus 2 u prime minus t times x prime. So I'm going to use this line. It becomes u prime times t plus u of t. Finally, plus x is u of t times t, and I want that to be 0. So let's just multiply everything through. Just like before, I'm going to expand everything out as far as I can and then collect terms. So this term becomes u double prime. T times t is t cubed. This becomes 2t squared u prime. Now for this one, I'm going to be careful. I've got a minus. T times t is t squared u prime. Multiply this, I get a minus t u of t. And then there's no change to this. This is u of t times t is 0. Notice these two terms cancel. 2t squared u prime minus t squared u prime becomes t squared u prime. So my equation now becomes u double prime t cubed plus t squared u prime is 0. Okay. There's only one derivative difference here, so I can use an integrating factor. So let's divide out a t cubed. So I get t squared over t cubed times u prime. Let me simplify that. So u double prime, this becomes 1 over t u prime. This is my p of t, so the integral of 1 over t dt is log of t. So my integrating factor is going to be e to that. E to the log of t is t. All right, so what do we have? We started off with our differential equation, t squared x double prime minus tx prime plus x is 0. I assumed a solution of the form u of t times t, and I plugged it into my equation. I got u double prime plus 1 over t u prime equals 0, and my integrating factor is t. So if I multiply everything through by t, I get t u double prime. This thing cancels, so I get left with u prime is 0. So the left-hand side becomes the derivative of t times u prime is 0. Is that right? So if I take the derivative of this, I get u prime plus t times the second derivative. If I take the antiderivative of both sides, antiderivative of the derivative is just t u prime. Antiderivative of 0 is just some constant k1. So that says u prime equals k1 times 1 over t. Oops, just 1 over t. Now if I take the antiderivative of both sides, antiderivative of the derivative is just a function. Antiderivative of 1 over t becomes k1 log of t, and then I'm having a new constant from that integration. So my solution now looks like u of t times t. U of t is k1 log of t plus k2 times t. Multiply that through, I get k1t log of t plus 2k2. And notice that is the same as my homogeneous function before, or homogeneous solution before, and I've got two unknowns, so this becomes the general solution. And the key thing is this was originally my sole homogeneous solution because I had a double root. And notice I am not just multiplying by t anymore. It becomes a lot more difficult.